This video is about prediction study design. It will go over the key concepts in how you design and evaluate predictive functions. Later on, in further lectures, we'll be talking about specific different types of prediction functions and their properties. The key ideas in this lecture are to talk about, first, the motivation for why you might do prediction, and as a motivation for how you might choose data and build a specific type of study. We're going to talk about the steps in predictive studies. It's a very common misconception that you just pick a classifier and that's the end of a prediction study, but it actually starts way before that and ends very far after that in terms of building a predictive function. We're going to talk about choosing the right data and how even if you have a bunch of data, it doesn't mean that you're going to be able to predict whatever you want to be able to predict in the outcome. We're going to talk about different error measures and the results of how the results of studies might change depending on which error measure you choose. And we're going to talk about study design, in particular about how to design a study so that you don't fool yourself when building a predictive function. So first of all, I'm going to talk about motivation. So one motivation is glory. And so, for example, there was the Netflix prize, which focused on trying to predict movie recommendations from other movie recommendations. And they were offered a $1 million prize for the people who could do this the best. This is a picture of Chris Valinsky, one of the winners of that prize. And of course, it's a good idea to work on prediction functions that will be of interest to a lot of people. In this case, it was interest to a lot of people, both because of the money and because it was one of the very first large-scale prediction contests. You might also be motivated by money. So, for example, the Kaggle contests that are currently running offer various different levels of prize money, but the biggest one is the Heritage Health Prize, which offers $3 million to the top team. Currently, the Johns Hopkins team, of which I'm not actually a member, is in the top 10, and hopefully they'll get all the way to number 1. Another reason is that you might just enjoy competing with other people, and so you can actually get data sets from Kaggle, which is a website that hosts prediction competitions, and it gives you the opportunity to build predictive functions and compare them to other people. Again, you won't have to collect your own data for this because Kaggle actually collects the data sets and cleans them for you. Another one that's near and dear to my heart is predicting to save lives or to help with human health. So Oncotype DX is actually a predictive function that's built on measurements of gene expression, and it can be used to help assign treatment to patients with breast cancer, and it's been shown to be helpful in improving patient care for breast cancer patients. So these are the steps in building a prediction function now that you're motivated to do so. So the first step is to find the right data. In the case of Kaggle contests or other prediction contests, the data will actually be provided for you. But in general, if you're building a predictive function, say for work or for a scientific application, a key step is determining whether you have the right data to be able to build a reasonable predictive function. And in general, it's not always true that just having a lot of data means you can predict anything that you want to be able to predict. Next, you need to define your error rate. This is actually another critical step that's often skipped over in building predictive functions. And it can have major consequences for the properties of the prediction functions that you end up choosing. So we'll talk about the different kinds of error rates and how they affect what your predictors will look like. The next step is to split your data into a training, testing, and optionally a validation set. And the reason that we do this, we'll talk more in the class, is because we want to be able to ensure that we don't overfit our data. In other words, we don't tune our predictive function too well to the data set that we have in hand so that it doesn't apply well to the next data set that we might be handed. I'll talk a little bit about why training and testing components of building prediction models are completely necessary and why a validation set is an optional and very good idea when you have enough data to make it a reasonable thing to do. The next step is to use the training set to pick the features that you'll be using in your analysis. Then to build or pick the prediction function, also on the training set. Finally, we might use the training set to cross-validate to either compare different predictive models or different feature selection techniques, or to get an estimate of the test set error if we don't have a test set at hand. If you don't have a validation data set, then you only apply your predictive function one time to the test set. You don't ever tune to the test set. You don't ever try to re-estimate parameters once you've estimated them in the training set. If there is a validation data set, you can apply your predictive function to the test set and provide minor refinements of your prediction algorithm. Although again, being careful not to tune too much to the test set. Then, if there's that validation data set, you apply your predictive function only one time. In other words, you only get one shot at proving the misclassification or the error rate that you get from your predictive function on the independent testing set, whether that's the test set or the validation set. So the first step is to find the right data. In some cases, this might be easy. So for example, if you want to predict what people will think about a new set of movies and you have a bunch of old movie ratings, it might make sense that you can use those variables very easily to make that kind of prediction. It turns out even in this simple case, it's not easy to build the predictive function, but at least knowing which data to use is pretty clear. In general, it may be a little bit harder. So I talked a little bit about that Oncotype DX example. There they used something called gene expression data, which measures the relative abundance of how much your genes are turned on or turned off to try to predict a response to disease, in this case, breast cancer. In that case, it was a little bit harder to choose which data set might be the most important. There are a large number of different measurements that you could take on a person to try to predict breast cancer, and it's not clear from the start that gene expression data will be the right one. So you have to be careful about picking which data set is the right data set to use for predictions. And in some cases, you have to know when to quit, when the data set that you have just can't be used to predict the outcome that you'd like to predict. This all depends pretty strongly on the definition of a good prediction. In some cases, having a predictor that's only slightly better than just flipping a coin can be a huge advantage, since there is no other good prediction algorithm out there. In other areas, where there are already a lot of very well-defined and very useful prediction algorithms, you might have to do a really good job to beat what's the current state of the art. An important thing to keep in mind is that in many cases, having more data or more accurate data beats out doing more complicated predictive analytics or predictive functions. So this is a link to a talk that's given about the unreasonable effectiveness of data, and it talks about how just having more and more data can dramatically improve predictive functions even when they're quite simple. Another thing to keep in mind is to know the benchmark. In other words, to know what you have to beat in order to be a useful prediction function. This is a really good thing to keep in mind whenever you're doing a predictive analysis, so that you don't get caught up thinking that you've built the best prediction function ever when there's actually 10 other prediction functions that beat yours. You need to start with the raw data for your predictions. In general, this is not true for study contest or for prediction contests like you might find on Kaggle or for the Heritage Health Prize. They'll often give you some processed version of the data set. But in general, when you're working on problems where you have to define the data that you're using to predict, you want to know if the processing that's done can affect your prediction values. And an important thing to keep in mind is that processing often happens across different samples that you might want to be able to predict. So if you get a new sample, you need to know whether you need to process it along with the old samples that you had, or whether you have some other processing approach that's independent of how many samples you have in your collection. So knowing the benchmarks is an important thing to keep in mind. So for example, if you have a binary classification, a probability of perfect classification in the test set, even if you used a random classifier, is 1/2 raised to the test set sample size. So if your test set sample size is only 1, you have a probability of about 1/2 of predicting the right answer, even if you just used a random classifier. If you have the test set sample size of size 2, the probability is 1/4, and so forth. So the reason why I'm telling you this is that if your test set sample size is too small, no matter how bad your predictor is, you still have a pretty good chance of getting all of the test set samples right, or getting a high test set classification accuracy. So the key point there is making sure you have a big enough test set to be able to truly distinguish a good model from just chance. In the Kaggle contest, they also give you examples of benchmarks so that you know where you stand compared to doing what would be considered very basic and probably incorrect analyses. So for example, in the Heritage Health Prize, you're trying to predict an outcome, and the outcome is quantitative. And they give you an example where if you predict all zeros, you get a particular error rate. And so if your prediction algorithm gives an error rate that's better than that, then you actually are beating what would be considered sort of the default simplest thing that you could do. It's always important to keep in mind that if you're not doing better than that, then you need to take a careful look at what you're doing and seeing if maybe you're predicting in the wrong direction, or if you're overfitting very, very heavily or something like that. Next, we're going to define some terms. So these are terms that are typically applied when you have a binary or outcome, or one outcome where you have one class that you're interested in and maybe one class that you're not as interested in. So a positive means that you've identified something from the interesting class with your predictive function, and a negative means that you've rejected the object and saying that it's not part of the interesting class. So a true positive is a case where you've correctly identified something as interesting. A false positive is something where you've identified it as being interesting, but it actually isn't interesting. A true negative is something where you've identified something as uninteresting and it really is uninteresting. And then a false negative is a case where you've identified something as uninteresting, but it should have actually been interesting. This language actually comes very naturally in the medical testing scenario, and so I'll give you an example of that because it might make a little bit more sense. So in this case, we're trying to identify, say, sick people with some particular disease using a screening test. So a true positive is the case where we've actually correctly identified the sick people. A false positive would be a healthy person that we've identified, that we've incorrectly identified as being sick. So it's a falsely claimed sick person. A true negative is a healthy person that we've identified as healthy. And then a false negative would be a case where a person that's sick, but we've incorrectly identified them as healthy. So in other words, we've said that they belong to the uninteresting, the healthy class, but they actually end up being sick. So using these terms, we can define some error rates, and these are the error rates that are typically used for binary classification. We'll talk a little bit about different error rates for continuous measures in a second. So here we have a couple of different cases. We have the test outcome. So we can say the test outcome is a positive or the test outcome is a negative. Again, think about this in the case of testing for a medical disease. So you want to, if the test outcome is positive, we say you're sick, and if it's negative, we say you're not sick. And then whether you have a condition or not is the true state of the world. So whether you're actually sick or not. So condition positive means that you actually are sick, and condition negative means that you're not sick. So again, if you are sick and we identify you as sick, we call that a true positive. If we identify you as healthy and you are healthy, that's a true negative. And then the two different types of errors that we can get are the type of error where you're healthy but we call you sick, or where you're sick but we call you healthy. Now these are the different ways that you can make an error, but you can also think about averaging errors over particular situations. So suppose that we tell you that you take the test and we tell you that you're sick. What you want to know is the probability that you actually are sick, given that we've told you that you are sick from the test. Now remember, we might make errors, so the probability isn't 1 that you'll be sick, even if we've told you that you're sick. So the way that we estimate that is the average number of true positives divided by the total number of times that we call you positive. In other words, the total number of times we call you sick and you are sick divided by the total number of times that we call you sick. Similarly, there's a negative predictive value, which deals with the case where the test outcome is negative. Sensitivity and specificity then deal with the cases where the condition is positive. So in other words, the case where you're sick and the case where you're not sick. So sensitivity ends up being the average number of times that you're a true positive, that you're sick and we call you sick, divided by the total number of times that you're sick. So in other words, the sensitivity is about the average number of people who are sick that we identify as sick. Specificity, meanwhile, is the average number of people who are healthy, in other words, that they're true negatives and we call them true negatives, divided by that we identify as healthy, divided by the total number of people that are healthy. So an important thing to keep in mind here is that sensitivity and specificity can help you define the average quality of a particular test in terms of identifying people. Whereas for screening tests, sometimes the positive predictive value and the negative predictive value are more useful because you're actually giving it to a person who will then have to interpret in their particular case whether that test is useful or not. So here's an example of why your choice matters. So in this case, it's a screening test for patients with bowel cancer. It's called a fecal occult blood screen test. In this scenario, we collected some data, and we identified 20 individuals who we screened and said that they correctly had bowel cancer when they did have bowel cancer. We had 180 people who we actually told that they had cancer even though that they did not. Then we had 10 people that in this case, we said that they did not have cancer, but they actually did, and 1,820 who were healthy and we said were healthy. So sensitivity and specificity are actually both relatively high. It's about 67% sensitivity. In other words, we catch about 67% of the cases where the person is truly has cancer. We identify them. And it's 91% specific. In other words, 91% of the time when you're healthy, we'll tell you you're healthy. But despite this, we actually end up with a very small positive predictive value. In other words, if you get a true positive test, there's only about a 10% chance that you actually have bowel cancer. And the reason why is there's such a small prevalence, or there's such a small number of people in the population that have bowel cancer to start with. So that means that there's a preponderance of samples that appear down here in this true negative situation and in this false positive situation. And so because of those numbers, you actually end up with a relatively small positive predictive value, even though you have a relatively high sensitivity and specificity. The take-home message, other than you might want to study this table to have an idea about what these different error measures mean, is that depending on your choice of error measure, you can have dramatically different results for the type of test that you want to predict. For example, if you built a predictor that, based on these numbers, you would think if you use sensitivity and specificity that it was a very good predictor, but if you use positive predictive value, this would be a very bad predictor and you might want to try something else. So some other common error measures are mean squared error, which we talked about least squares when we were talking about both k nearest neighbors and when we were talking about regression. And so this is an error measure that's used for continuous data. It's often sensitive to outliers. You might also use something like the median absolute deviation. So that's also for continuous outcomes, and it may be more robust. Then there is sensitivity and specificity, which I talked a lot about on the previous page. And sensitivity is also often sometimes called recall. You can also look at accuracy for binary data, which weights false positives and false negatives equally. Or you can look at concordance. So concordance is a term that's used when you have multiple predictors and you want to know how well they all coordinate in making predictions. And so I've linked here to one example of a concordance measure. So now I'm just going to briefly talk about the study design. So this is actually the study design that was used in the Netflix dataset, and it's actually become sort of the standard study design that you would use for predictive functions, say in something like Kaggle. And it's useful even if you're going to be building your own prediction data sets because it gives you an idea of what you should hold out and how you should build your classifiers. So they started off with 100 million user item pairs, and they divided that into two data sets. One was the training data set, and one was a held out data set. So the held out data set was not provided to the people that were building the predictive function at all. And so then they split this into multiple data sets. So in their case, they built it into a test set, a quiz set, and a probe set. So in general, you might just split this into this held out set into two sets, the test set and the validation set. But here they did it a little bit more complicated. They then provided the labels to people of the training data and the probe data so people could train their models on the training set, then apply it to the probe set and see how well they were doing. When they then submitted responses to Netflix, Netflix tested them on the quiz set and returned an error measure telling them how well they did on the quiz set. Not until the very end, when the entire competition was over and that they were trying to determine the winners, did they apply the predictive models to the test set. This set was held out until the very end so that people couldn't overfit their models to any particular characteristics of this test set. It was a completely independent set of data. If you go and read this paper, it tells you a little bit more about the design of this study. But to give you a little bit about the reasons why we would design the study this way, so the training data is what's used to build the predictive function. We can do whatever we want with the training data while building the predictive function, and we may end up overfitting. And by overfitting, I mean we might tune our predictive function just perfectly to this data set. We can then evaluate that on either what's called the test data set by evaluating it on a data set that was held out. And so we don't know the labels of that data set, and we can't train our model to apply it to that test data set. But there always has to be one data set that's completely independent, that was not used in any way to test or train or tune your model, that can be applied, that the predictive function can be applied to at the very end of the process to evaluate in an unbiased way what the error rate of your predictive function is. So here are some key issues in building your models. You want to think about the accuracy and overfitting. So accuracy is you want to get the predictive model to be as accurate as you can. Overfitting is you don't want to tune it too carefully to your data set, hence you have that study design that allows for held out data. Another important consideration is interpretability. Often predictive functions are going to be used by human beings, for example in the medical testing scenario, and so you might want a predictive function that can be easily interpreted. In some other settings, you don't actually care about interpretability if, for example, the prediction function is going to be used only by a machine in a deeper analysis. You might also want to think about computational speed, as some of the best predictive functions also are computationally slow. Here are a couple of different resources for more on machine learning and in particular on predictive functions. So you can look at the Practical Machine Learning lectures from Hector Carrata, Bravo, or you can check out the Elements of Statistical Learning, which is a free textbook from the folks Tim Sharani and Hasty. You can also check out the Coursera Machine Learning class offered by Andrew Ng, or Machine Learning by Hackers by Drew Conway and John Miles White.